Good morning, everyone. My name is Nadav Samet. I'm the CTO and one of the co-founders of a company called TrueAccord. It's a Silicon Valley-based fintech startup that's using Scala. Before TrueAccord, I spent many years at Google working on various projects like Gmail, Google Apps, and Google Travel. And like everybody else at Google, I spent a lot of time writing and using protocol buffers. So in today's talk, what we're going to do, we're going to do a gentle introduction for protocol buffers. I'm going to take you from a beginner to an expert in 7 minutes. And it's really possible. And I'm going to show you how a little library called ScalaPB makes it really easy to use protocol buffers in Scala, and why you should care and why you should use protocol buffers. And at the end, we're going to have a live demo that's going to show you a full app using protocol buffers all the way from a Scala.js web app to a Play Framework web server to a Spark streaming aggregation server. And this is going to be a really amazing demo. I've never done anything like this before. It might fail miserably. So we're going to find out together. So here's a story that may sound familiar to you. We had it at TrueAccord. When you just start a project, there are a lot of business requirements keep coming in that keep changing your data model. So for example, in our case, we had users and we had accounts. And in the beginning, every user had exactly one account. But over time, we discovered that some users need to share a single account. And sometimes there is one account that there are users that need to have multiple accounts. As every time that those changes came, we followed by rolling out SQL migrations. And as you all know, rolling out SQL migrations to a live distributed system is a pain in the ass. That's a technical term. So the idea was to move away from storing columns in MySQL that represent individual values and use a key value store to store serialized versions of documents, store all entities as values in a key value store. So let's zoom out a little bit and talk about the protocol buffers, which is the approach that we're using to store our entities. So how many people know what protocol buffers are? Pretty good. Great. Almost everybody. How many people use them in Scala? Few. Right. About half people in the room. So cool. I'm going to give some introduction. And I know that most of you already seen some protocol buffers at some level. I think it's still going to be interesting to look at some of this angle. So let's start with just defining what protocol buffers are. So protocol buffers is a mechanism that was developed at Google to represent structured data, messages, like case classes. And it comes, the specification also says, dictates how those messages are going to be serialized as bytes, and how they're going to be parsed from a byte stream back to the messages themselves. And it also ships with a compiler that generates code for you. It generates serializers and deserializers for you in Java, C++, and Python, but unfortunately not in Scala, so I had to write ScalaPB. So one cool thing before we jump into what protocol buffers look like, you can already see, is that the beauty here is that the protocol buffer language is agnostic of your platform. So you can serialize message in Python and read it in Scala, or the other way around, between basically any pair of supported languages. So here's what a protocol buffer schema looks like. We're using in this talk syntax equals proto3. It's the latest specification of the protocol buffer language. And this is an example of a message called person. It has a first name, which is a string, a last name, which is a string, and an age, which is a number. And every field has a unique identifying number with it. So once you have this schema, you can use the Proto-C compiler, which is built by Google, that generates the serializers and deserializers for you in various languages. And if you're using ScalaPB in Scala, you can basically ignore all of that and just use SBT compile. It would generate the code for you and compile it in a single step. And that's how it's kind of integrated in your development flow. If you go back and change the protocol buffer, you just do SBT compile as normal. So you have this protocol buffer, and ScalaPB would generate for you a case class for it. So you basically get the same thing, just in Scala. And you deal with it like any normal case class. You just can initialize it and put some values for each field. And then you can call 2-byte array, and that would give you a stream of bytes. This is basically the binary representation of this message, which is very compact, only something like 15 bytes for this one. And you can also do the opposite. You can start from a series of bytes, from a stream of bytes. You can get it from the network or from disk or from your database, and call person.parseFrom, which is a method that is automatically generated for you, and it will give you back the original fields that you got, the original case class. And another cool feature of protocol buffers that make it that makes it really good is that you can create complex messages by composing simpler ones. So, for example, here we have an address message which has a street and city fields, and a bank account message which has a routing and account number. And then we can make a person message that has an address field, the address that we just defined above, and a list of bank accounts. And then you can just, if you just store this person in your database or use it in your data processing pipeline, then you don't need to deal with those many-to-many fields like you'd normally have, like this relation table that you'd normally see in MySQL. This is the generated code for that. So basically what you'd expect, you get a case class for the address, a case class for the bank account, and a case class for the person. And the person has the address field, which is an optional address, and a list of accounts which defaults to the empty list. Now, cool thing to know, especially if you're already familiar with protocol buffers, is kind of like dive deep into the wire format, which really helps you understand why certain things are possible with protocol buffers. So if you have this person message, and we initialize it with those specific values, John Smith and age 34, and we serialize it, what you actually get on the wire is something that looks like this. Basically, we have the field number followed by a value, field number followed by a value, and another field number followed by a value. So if you think about it, you basically see how if you compare it to something like JSON, where on the wire you send a lot of punctuation and the field name itself, like with in quotes and all that. Here we only send a binary representation of the field number. And beyond the saving, the cool thing about it is that you can rename your fields over time. So let's say that you discover that you had a typo, or you want to change the terminology that you're using in your schema. You can just change it, deploy that server, and it can still exchange messages with the old servers that still have the typo or the older name. And those systems can keep talking with each other because the wire format, the binary representation, is not impacted by the rename. Another cool feature that is very useful if you're doing rich data and a lot of business logic with the protocol buffers is using ENUMS instead of strings. So for example, here we have a bank account protocol buffer, and we want to have some indication of which account type it is, a checking account or a savings account. So we define an enum, and then we can refer to that enum in the bank account message. And that leads to a very idiomatic Scala code. So when that gets generated, we get a seal trait for the account type, which is basically the base class for the account. It has two predicates, is checking and is savings, which are Boolean. And you get two case objects for each possible value of that enum. And the cool thing about it that it leads to a very nice usage when you actually write your business logic. Say you have a B bank account, you can do b.account type is checking and do some logic if it's a checking account, else do something else. And moreover, you can use a pattern matching and write a case for every possible value. And the cool thing about that is that beyond that, it's very idiomatic Scala, and it's so much better than comparing with hard-coded strings for every possible account type if you use something like JSON, is that the compiler will actually save you. So if somebody ever adds a new account type and you recompile, the compiler will give you a warning for every pattern match that's not exhaustive, that you haven't specified what to do. So the compiler has really helped you to write code that is gonna handle all the cases. And it's really, in our experience, it's been great to have a system that evolves and gets more complicated over time. by creating a lot of structured data like this. So now that we are protocol buffer experts, let's compare that to, just summarize what we just said and compare that to a simpler, more common JSON approach. So we have an efficient binary format. Every key, every value is stored serialized in a compact binary representation. It's easier to programmatically access the data, so you're basically working with case classes and idiomatic Scala rather than, in the JSON case, if you ever had to work with JSON, it all the time feels that you're navigating a tree of strings going down to get the value you want. And you actually know what to expect. You know what to get in every field. You know which type you're going to find. So you get the type safe in a process communication. So if you have two servers that are talking protocol buffers with each other, the two servers know what types should be in every field. They know the format of the message. There are no problems at runtime that like you'd get with the more of the dynamic formats. What I found really, really beneficial is when your project grows and you have a front-end team and a back-end team and a data science team, and they can all reference the same protocol buffer schema and develop against that. So there's a single place that all the teams can look at, and there's a documentation what fields mean, what is the semantic meaning of every field, or what like the special values for that field. What does it mean if that number is -1? What it means that if this message is absent, and so on. So creating this single place where the entire organization, the entire project, even if it's divided to multiple teams, has been proven to be very helpful for us in scaling our business logic and the system grew more and more complicated. And the last benefit for protocol buffers, it's great for evolving schemas. It's so easy to add more fields or remove fields and make changes without breaking your running system. So let's take a look at one example. So let's say you have this parcel message that we keep referring to, and you notice that you store the age. And then you realize that it's not a very good idea to store the age of the person in your database because the persons keep going up. And what you really want to store is the date of birth or the year they were born. So no problem. You basically just create a new protocol buffer. You basically add a year of birth field to your protocol buffer. And in the service you just deploy, they can still read the old field, but they have access to the new one, which it would be 0 by default. And then you can basically provide a function that would try to get the age from the year of birth, but if it's unset, if it's 0, it would fall back to the age. And over time, what you can do is to write a data migration, basically a simple script that would populate the new field and eventually drop the old one. And because it's so easy to add and remove fields, those operations can just be rolled to a live distributed system without any downtime. This is just an example of like a toy schema evolution, but you can do a lot of stuff. You can add fields and remove fields, like we just mentioned. Everything is optional. So the parser of if you remove a field and you try to parse something and you get the old version of a message that had that original field, your parser wouldn't crash. It would just drop it. You can rename fields, like we explained before, and you can convert between compatible types. You can convert between int32 to int64. You can convert back if you don't mind losing a few digits. You can convert between strings to byte arrays, from byte arrays back to string if they're UTF-8. There are a few rules, but you can do a lot of stuff. And you can also convert between a single field to a repeated field and back. I want to talk a little bit about the motivation for writing ScalaPB. So protocol buffers ship with Java support. And because they're in Java and they don't have case classes, they use builders. And this is a little bit painful to do, especially when you have nested structures. So basically, you get a person builder, and you set a few fields. And then you need to get a nested builder to set the nested fields. And then you call builder.build. And it gets very cumbersome when you have a few layers of depth over there. You need to store the builders in temporary variables, and it's not really nice. Another thing is that they started to build their API before Java got the optional field, before Java 8. So they provide this as address or as whatever methods to let you know if a field is present in a message. And this leads to a code that you basically all the time try to lift those fields to options. So this is what made me start ScalaPB. And the goal was to make it easy and idiomatic to use protocol buffers in Scala. I want to use case classes. I want the development flow to be integrated with SBT, so I can easily change my protocol buffers and not worry about distributing proto-C to all the developers. I want to make it easy to make updates to nested fields. And by the time we created ScalaPB, we already had tons of code with the Java protocol buffers. And it was really important to be able to, nobody's going to move from Scala to Java, from the Java protocol buffers to Scala overnight. You want to provide a way to make it gradual. So ScalaPB can generate conversions between the Java protocol buffers and the Scala protocol buffers and back. So you can basically convert part of your system to use the Scala protocol buffers and basically have those converters as a barrier between the old code and the new code. And eventually you move more and more code to the other side, to the Scala side. You can actually use it to do the opposite direction, but I don't recommend that. So, and then as the project got more and more successful, we got users told us they're using Scala protocol, using ScalaPB in all sorts of contexts that we weren't using at the time, like in Spark, and for akka and gRPC. And it was clear that if we want to make this project successful, we've got to help users work proactively in those environments. So that we invested a lot of time in creating adapters, creating documentation for those environments. And some users started to contribute. So some user just one day sent me a pull request for a gRPC support for protocol buffers. So thanks, Kenji, if you're watching this. And beyond that, we also learned is that Scala users really like to have a lot of control over the generated code. So we provide a lot of tweaks, a way to tweak, and a lot of knobs to control the types and certain aspects of the generated code. For example, we allow you to specify custom types. So if you have this, let's say that you have this click event that you're using to track clicks on your web app. And it's very common to store the time as in64, just some representation of milliseconds since epoch. And however, when you're doing this, some higher level code, some data analysis, you'd usually want to work with a higher level type, like something like datetime. So you can tell ScalaPB to use org.time datetime when you work with it on the Scala code. So ScalaPB would just take that click event, and the case class would have the datetime field for the timestamp millis. And the cool thing about it is that this is completely transparent to you as a user. When you have this case class and you serialize it, it would be converted to an in64 and sent over the wire. When you get a message, no matter who encoded it in Python or Java, it would take the number and convert it back to a datetime. And all that magic happens, all you need to do to make that magic happen is to provide an implicit value called type mapper that tells ScalaPB how to convert between your type and the original type. The last thing I want to talk about on that ScalaPB provides is nested updates. So this is a classic problem with the case classes and immutability. So let's say you have an A that has a member B, you have a class B that has a member C of type C, C as a member D of type D, and D finally as a E, which is an integer. And you are giving this A from the outside, and all you want to do is to change the E that's kind of nested deep inside it. You want to set it to 17. So here is the code that you normally need to write. You need to take A and make a copy of it, and that A needs to have a copy of A.B, which needs to have a copy of A.B.C, which needs to have a copy of A.B.C.D, with E assigned to 17. Obviously, you never want to write something like this. This is not fun, right? And this is especially infuriating if you compare it to what the guys that do imperative programming can do, right? So with ScalaPB, you can use this technique called lenses that lets you do those mutations in a very elegant syntax. And ScalaPB ships with a small lenses library that lets you do nested assignments, but also transformations like calling to uppercase on a nested field, or concatenating to a list, and this way you don't have to to make those cumbersome copies. And also, even in this example, we're scrubbing sensitive data. We're scrubbing account numbers by iterating over a list and assigning something to each member of a field. So this is a pretty cool way. And if you try to write this with copies, it's really, it's not fun. So now demo time. So the demo is that I'm going to do, I thought, it would be nice to do a survey of which programming language is our favorite language. But because this is a Scala scale by the bay, I kind of can guess what the answer is going to be. So I thought it would be interesting to actually, that we vote on our least favorite language. I think that would be way more fun. And to make it even more interesting, the survey is also going to include your age. So we can see what is the least favorite language for each age group. And I think it's going to be really interesting to do that. So what we're going to build is something like this. We're going to define a protocol buffer that's going to represent the vote. And we're going to have a Scala.js client that's going to render a UI for you that you can vote from. You'll be able to vote from your mobile phone or your laptop. And I'll give you the URL in a bit. And this would go to a Play Framework web server, and which is going to deposit the votes faithfully in Kafka, which is going to be our message bus. We're going to have a Spark streaming server that's going to subscribe to the topic in Kafka and going to aggregate the vote, put them in Redis, so Play can again show them to us in real time on a dashboard written in Scala.js. So can we do it in kind of 10 minutes? Let's try. So, all right. So yeah, I'll need help here with the mic. Yeah. So I'm going to switch to IntelliJ. OK. So here I'm editing the protocol buffer that we're going to have. So let's write a message called vote. And we're going to define an enum for the language. And let's have some value for unknown, which, these are for a default value that we have to provide. And I want to hear from the crowd which language you want to see here. What, assembler? Assembly, right? What else? Erlang. What else? Lisp. I heard Lisp. What else? Bash. Bash. OK. One more. Let's have one more. Pascal? Pascal? Haskell. OK. That's going to be loaded. OK. So now I just defined the type. Now I need to have a field that's actually going to have this type. And we said that we want to also take your age. So here we go. And now I'm going to go to my shell. And I'm going to compile this protocol buffer. Good morning, SBT. I'm going to also start the server in the meantime. Let's see if we already have the protocol buffer generated for us. Yes. OK, so we have a final case class vote, and it has a language field. And let's click on this. We see the silt rate with all the languages that we just chosen as predicates here. And basically, we see here the case objects that were generated for that. So pretty cool. And what I also prepared in advance is the Scala.js UI. I will not dare do Scala.js in kind of like in front of a live audience. So it's kind of risky, right? So so basically what we have here, we're using the awesome Scala tags library to generate the UI, the HTML. We have form, and then we basically iterate over all the possible language values, filtering out the unknown language. And we're yielding a div that has a radio button for every language. And when the form gets submitted, we are basically serializing it to a byte array and making an XML HTTP request to the backend. So let's try it out. OK, so I'm going to give my answer. Not really, but let's try. So not implemented yet. And the reason is that basically this answer goes to the backend, which doesn't have an implementation for this action. So let's look at the root controller. It here's the submit method. And here we tell play to basically take the body and implement it as a protocol buffer. So we can have a vvote equals request.body. Sorry. And we can do v.language match and have IntelliJ help us, complete the code for all the languages. So it's really nice, that the IDE can help us because it's all very structured. But let's do this. If the language is unknown, we're going to give a bad request. Pick a language. Else, if the age is invalid, age, or you're too old, let's say invalid age, and then else we are going to say thank you. Let's try that. So here's my kind of like 1 minute form processing. I'm going to give a language but not an age, invalid age. No, a language, pick language, but if I pick both, thank you. So the last thing I'm going to do is I'm going to tell it to, if the vote is valid, I'm going to send it to Kafka. And basically, this is the vote is the topic name, and I'm serializing it to byte array. And let's deploy it to my server. Yeah, it looks like it's starting. And in the meantime, I'm going to show you how the votes are going to be aggregated. So we have a Spark streaming Spark streaming application here that subscribes to Kafka and gets all the votes as bytes. The next thing it's doing, it's parsing those votes from bytes back to case classes, back to protocol buffers. Then it's mapping every vote to a key value pair where the key is a tuple. It's the language and the age group. How do I get the age group? I divide by 10 and multiply by 10. I'm basically rounding it down to the closest multiple of 10. So basically, all the votes now are keyed by the language and the age group. And I'm using a function called update state by key. So I basically want to count how many votes I have for each key to a language and an age group. So the update state by key gets a parameter, which is a function, which is a new sequence of vote that has the same key. So they are basically need to be counted together. And the old count, which is called current stat, which maybe it's an option of an integer. So the first thing we do is get or else 0 of it. So that's the default value, 0. And we add votes.size because this is the list that I'm getting of the votes that have the same key. And finally, once I have this aggregation, I write a little bit of code to store it in Redis. That's all there is to it. So, whoa. Looks like we have, like I need to do this again. It's a complex demo, I warned you. So, and in the meantime, it would be great if you could take your phones out and go to demo.thesamet.com, and I can show. I'm going to give you a QR code. It's going to be here in a second. Here we go. So you can scan the QR code if you want to get the URL. It's also written below. Yeah, the votes are coming in. Beautiful. And in the meantime, I can also take questions if there's time. Yes? Yes.
So I've used ScalaPB a little bit to check some stuff out, and one thing that I noticed with version 3, everything is optional. There's no more required fields.
Right.
It generates all of your case classes. Everything's an option, right? Which becomes kind of problematic for doing algebra on your case classes because you have a layer of indirection for everything. Do you use version 2 for required fields to get around that? Do you think that version 2 is going to stay around for a long time? And if I choose version 3, how do I make that better?
Okay, thanks for the question. So the question is, how do we deal with the required fields in Proto 3 when basically they are out of the spec? Is Proto 2 still going to stay around? And I guess that's kind of the gist of it. So yeah, so Proto 2, as far as I understand, is going to stay around. There's tons of protocol buffers out there and tons of users that are still using Proto 2. And there's no really a very good reason to break them. So all the time when we use Proto 2, there was this notion of don't use required fields, they're evil. They basically make it very hard to do those migrations because you can't remove them from your parsers. This is basically something that, the push was always to get your validation code to be outside the protocol buffers library and have your application validate if a field that you really want is in the message and not rely on the parsers and the serializers to tell you that your message is valid or not. In Proto 3, basically, you lose this option. And it's a little bit worse for some users because all the primitive values are default to zeros or empty strings, so they lose this even distinction between none and some 0, right? So there is a solution for that that Google is shipping called well-known types, which is basically wrapping all the primitives inside messages, and the messages can be they are really still optional. And then again, you have to use your application logic to enforce that they're there. Yeah. More questions?
So let's say server is communicating with protocol buffers. If it was JSON, it is easy to use Postman or something to see what's the response, what's going on.
Yeah.
How does that work when you use protocol buffers?
Yeah. So in protocol buffers, you basically, if you're using Scala.js, for example, so the question was, what happens to debugging your server if your frontend is using protocol buffers, if your wire format is binary, basically? Because in JSON, you can use the developer tools and click around and see. So yeah, this is true. This is basically, there is a missing tool. I'd like if somebody would just write a Chrome extension that can pass protocol buffers over the network. I don't think it's hard to write it. However, there isn't something like that, and we resort to printlns when we need to debug things. Yeah. I couldn't hear you.
What are you doing for any support in Proto 3?
So for any support, we do have the.
It's kind of ugly to deal with it.
Yes. So basically, any is so the question is what we do with any support. The any is a type that basically it's kind of a dynamic variable that you basically get. It's a message with two fields, the type that it's supposed to be, and I think then a byte array. And the byte array is interpreted in different ways based on the on some URL that you're given that represent the message. So we have some support in ScalaPB for that. If the message is known at runtime, you can basically get there is an implicit conversion available on any that can give you the actual type. But you need to know what to expect. I think it involves using as instance of, and it's not great, but that's what we can do, right? The one-off, you mean?
Yeah, one-off. Yeah.
Yes. Yes, there is something called one-off, which is it's a nice feature of protocol buffers. How many minutes do we have?
5.
5, cool. So I can show. I have a backup slide for this. If people are interested. Yeah, so here, for example, it's another way that protocol buffers give you a very powerful way to structure your data. So for example, you have a payment event, and you want to store, you want to say how the payment has been made. So you might have a message credit card, and we have the bank account that we defined in an earlier slide. And then you can have a one-off payment type, which is like a union. It's either this or that, but not both. But it could also mean none of them. So you have a payment type with a bank account or a credit card. And ScalaPB would also give you a sealed trait and two case classes that extend each of these options, it's really cool to write logic like that. But this is a way to basically have the parser give you a little bit more, validation before the message is ended to your business logic. Yeah.
In your experience, what are the kind of problems have you encountered using protocol buffer end-to-end?
The question is what problems we had working with protocol buffers. I can't think of any. Actually, it's a great question. So, the one thing I'd say that when you write something like this, it makes it really hard for somebody. Like, let's say you have a backend and a frontend speaking protocol buffers, and you just want to send, like if it was JSON, maybe you just push like underscore color hidden field that nobody knows what it does except two guys that are implementing it. You can't just push random stuff with the protocol buffer. It's basically rigid and it's locked to that schema. So it could be good or bad thing, but basically it doesn't allow you to kind of like throw temporary variables inside it for some ad hoc use cases like the color of the UI or whatever. So sometimes it kind of like stops you, but maybe in the long run it's a good thing.
Follow-up question.
Yeah.
Is it possible to use protocol buffer with front-end technologies like AngularJS or React Native or anything?
Yes, yes. This is basically, here we use a Scala. What? Yeah, the question is whether it's possible to use a protocol buffers with AngularJS and other front-end technologies. So I don't have a lot of experience of mixing JavaScript with Scala.js. However, there is a protocol buffer code generator for JavaScript that Google provides that can basically, if you already have your front-end in JavaScript, you can use that. Yeah.
How is it compared to Avro?
Yeah.
Other big data projects like Storm, Hive,
Yeah.
Kafka?
So so the question is how protocol buffers compare to Avro. So it's very similar. There's more common things that are different. Avro tends to be more dynamic. So the schema is also, I believe, included with your documents also, and it's more symbolic. So you basically don't have this when a message is represented. I think it leads to. I don't have a lot of experience with Avro, but I believe that things like rename are resolved symbolically at runtime rather than at the wire format. Yes.
It's very different. Protobuf is ordinal based, Avro is position based.
Yeah.
The difference.
Yep.
Unless if you use it as parsing.
Cool. Yeah, I'm seeing that Bash is getting a lot of 8 from users, 20 to 40. But I see like a lot of old people in the room, like 110 people that don't like assembly, and I can understand that. So cool. More questions?
Does so you can get JavaScript or JSON serialization baked in too, correct?
Yes.
Tell us a little more about that.
Okay, so the question is about JSON conversions for protocol buffers, which is something we still use a lot. Basically, you can convert a protocol buffer to a JSON and back, and you can then this gives you the option to write your front end with the normal JavaScript technologies without using Scala.js. It works pretty well. Like we use it all the time. Yeah.
That's only for those 3, right?
You can do it also with there is a ScalaPB JSON4S library that we wrote that lets you do it for any version. Yeah.
One question.
1 minute.
Did you ever persist protobuf as serialized bytes to disk and make it to what format?
Come again?
Do you ever persist protobuf bytes to disk? You save them to a file.
Yeah. So basically, you have a methods that write them to an output stream. That's kind of the easiest way to get them to anything.
Or like if you need to use it in HDFS, like there's a block file.
Yeah. Yeah. As long as you have something that can speak the output stream abstraction, which is probably everything, then yeah. At the back.
To use it in Spark, do I have to first convert
You can use case classes directly at Spark. In Spark, there's nothing that you need to do. You might want to enable a cryo serialization that's more efficient. And there's actually, I'm going to post a sample on how to do that. There's a way to do it. So that's all the time we have. I'm going to be hanging around here if anybody wants to ask me any question offline. Thank you.